Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Hi, welcome to the Space Policy Show. We have Dave Lubar with us today, and he's here to talk about developing a sustainable spectrum approach for 5G services and critical weather forecasts. Again, I just want to remind you, please join the chat. There's a button to your right. You just click, you put your name in, and we'd love to have your questions and engagement. At the end, we may have a poll question or two, so be on the lookout for that. Also, I just want to remind you, we're here every Tuesday and Thursday at 1 p.m. Eastern. We're so excited that you're here. Again, we do record these episodes. You can find them at aerospace.org/policy. There's a button that says Watch the Space Policy Show. Thank you so much for joining us. And Dave, over to you.
Well, thank you, Rebecca. I would like to thank our participants for attending this webinar event for the Aerospace Center for Space Policy and Strategy. Before starting this topic, we hope your families are safe and in good health during this global pandemic. I'd like to confirm real quick with the moderator that you are getting the slides out on the feed because I still see the video. My name is David Lubar from the Civil Spectrum Management Group at the Aerospace Corporation. We would like to focus on remote sensing and how passive measurements function in order to help understand the spectrum ramifications of emissions from nearby broadband wireless in the frequency bands above 23 gigahertz. These materials were first presented at the annual meeting of the American Meteorological Society by either yourself or by Dr. David Kunke of Aerospace during January 2020. I will preface my remarks by saying that I do not speak for any federal agency or external organizations. Let's have the next slide. This next slide begins with a graphic showing a non-geostationary weather satellite taking passive measurements. And as you start the video associated with it, a weather satellite flies overhead, detecting the weak natural emissions of the atmosphere by passive sensing. Once terrestrial infrastructure is built and activated in a dense urban environment, the out-of-band emissions from such 5G systems can effectively mask the natural signals that occur in the atmosphere. 5G towers work to track users, incorporating techniques such as RF beamforming, and that signal would bounce off the ground or off buildings and terrain, and some portion moves in an upwelling direction. It is this adjacent band signal which can cause radio frequency interference to a satellite-based passive sensing instrument. Let's have the next slide. Now, not all passive bands are near the planned 5G usage. In this table, a subset of the frequencies used for passive remote sensing between 15 and 100 gigahertz are shown. The table lists passive bands in this overall frequency range. After extensive discussion and negotiation at the International Radio Communication Union, or ITU, World Radio Communications Conference, which was held last fall in Egypt, international regulators selected only 2 millimeter wave bands that were near passive remote sensing out of a total of 5 band candidates for 5G. That would be 24.25 to 27.5 gigahertz, and 37 to 43.5 gigahertz. They're shown in red on this slide. Therefore, it is important to note that not all 5G bands will impact passive remote sensing used by the weather community. Yes, there were some headlines in various publications that didn't clarify this fact, but many 5G bands are not near frequencies used by the meteorological community. Let's have the next slide, please. There are other services in these frequency ranges which can contribute to the overall interference budget into passive bands. Now, I will not brief this chart. No, I suspect you could read this chart over the webinar, but I just want to note that the 24.25 to 27.5 gigahertz band and the 5G band, which begins at 37.6 gigahertz, are circled in red. Let's have the next slide. Now, some of the next few slides address answers to questions that were posed in our recent Aerospace Corporation issue paper. And if you're interested in that, I'm sure our commentators will be able to point you to where that's located on the web when we're finished. Why can't the satellite simply move to another frequency band and get away from the 5G signals? Well, the properties that the satellites are measuring originate from the natural physical phenomena properties of the atmosphere. We can't ask the planet nor the atmosphere to change the very narrow range of frequencies that provides this unique characterization of natural phenomena. It's also important to note that not all weather organizations utilize these bands in exactly the same way. For example, the Europeans use the 18 gigahertz, the 26 to 24 gigahertz band, and the 31 gigahertz bands together to correct data that's taken in other passive bands. NOAA creates some distinct operational products from the 24 gigahertz data, but does not use the 24 gigahertz band for direct inputs to numerical weather prediction to the best of my knowledge. Can I have the next slide, please? One other issue that raises its head on a very regular basis in this whole scenario are, do satellite sensors, in this case for passive, work the same as receivers? And the short answer is a resounding no. And this is a very important consideration. So as we review the technical discussions associated with the high-band 5G versus passive sensing topic, we note that a radio receiver and a satellite-based radiometer work quite differently from each other. It is clear that communications receiver protection techniques are not especially applicable to these satellites. And the reason is these satellite instruments, as they are not receivers. The radiometers are very sophisticated power meters. They do not detect information content. So let's look at this illustration we have on the slide. I think that will help in understanding. This illustration shows one large signal riding above the noise floor. The large signal could contain information content that could be recovered by a receiver and converted into voice or digital data files. Now, the noise floor is a threshold below which information content is rarely carried. If any unwanted byproducts from a transmitter are generated by a communication signal that falls below this noise floor, the receiver typically ignores them, and there would be no impact to information transfer in a smartphone or other device. But the radiometer in the satellite payload, it is measuring the minute raise and fall of the noise floor. That's what you detect, those unique natural properties of interest. Its measurements are made over a wide area, and in some cases for a much longer time duration than what is needed for a communication signal such as LTE resource block. The microwave instrument on NOAA's polar orbiting weather satellite, for example, has a dwell time of 18 milliseconds. This would encompass multiple communication signals that occur in a vastly shorter time duration. So the portion of a communications signal byproduct that falls out of band would change the level of the noise floor, or in other words, contaminate the accurate measurement of any noise floor fluctuations. It would in fact mask the small natural signal levels that the weather satellite instrument was trying to detect. Let's have the next slide. So what happens if the weather satellite sensor contamination levels vary? So a low level of out-of-band emissions would likely pass through the various quality checks that are downstream from the measurement and not reveal that it had contaminated the passive sensing measurement from the satellite instrument. So that data would likely get through and we would know that that had happened. A moderately strong out-of-band emission signal would be identified as interference, and the resulting data measurements would be eliminated, providing no input data for those specific points in the output data. There's no actual mitigation for the contaminated data measurements. Simply, in some cases, bad data would be removed from the sense information and just discarded. And since no one can predict what the ever-changing atmosphere is doing in advance, there is no methodology that could guess what the natural emission levels should be. Let's do the next slide. So there are a number of international limits that have been discussed. There have been multiple articles, news reports, and congressional correspondence about the impact of different interference levels into the 23.6 to 24 gigahertz passive band. Now, I'm not going to rehash all the various viewpoints and discussions, but perhaps I can help make some sense of all the values discussed in these documents. After all, most people that don't work in this area have no idea what 37 decibel watts reference to a bandwidth even means. So this slide shows a graph, and it was constructed by Dr. David Kunke of Aerospace. And this shows various interference protection levels overlaid with the levels where interference can impact the space-based passive sensor. So the x-axis of this graph shows the density of 5G transmitters over a square kilometer from 1 to 100 on a logarithmic scale. Now, since we don't know the actual density of 5G transmitters per square kilometer for installations that have yet to be built, it's not known what the cases are. It would be useful then to show this variable to fit multiple cases. This graph, like any assessment of this issue, is based on assumptions. Now, the shaded areas on the y-axis represent the values where the interference threshold of the NOAA Advanced Technology Microwave Sensor, or ATMS, is exceeded. ATMS is the payload on the Joint Polar Satellite System, the primary non-geostationary polar weather satellite for NOAA. The pink color would be where the sensitivity begins, called 0.1 degree NE delta T, after which above in that pink area, the sensor would detect information that would upwell in its direction. The gold area below it is the more conservative ITU recommendation value of sensorability. So then let's talk about these lines. The values on the plotted lines then represent out-of-band emission values in decibel watts, reference to 200 megahertz. There was a compromise approach decided at the ITU as an international recommendation last fall for out-of-band emissions into the 24 gigahertz passive band. Cell towers would have a value of minus 33 decibel watts as an out-of-band emission limit until 2027, where then a more stringent minus 39 decibel watts apply, and a similar provision for handsets. So, and that's the international guidelines in the radio regulations. Domestically, the Federal Communications Commission in Auction 102 that was held in mid-2019, they levied an out-of-band emission level onto the 24 gigahertz passive band of minus 20 decibel watts, which is 20 times stronger than the proposed minus 33 decibel watts value from international venue. So if you're now confused by listening to all those numbers, let's try it and look at it somewhat on these charts. At the minus 33 decibel watt value, that's the orange line, the second from the top on this graph. That's the base station limit in the 24 gigahertz band. So less than 10 transmitters per square kilometer will reach the 0.1 NE delta T sensitivity threshold of the sensor. And even one transmitter would touch the more conservative ITU interference threshold value of minus 166 dB watts. So in a square kilometer, looking down from space from the sensor, you would see that signal if there was only one transmitter, basically. In other words, whenever the value is, it crosses that pink threshold. So the WRC 19 more restrictive emission value of minus 39 dB watts, which goes into effect in 2027, is the gray line. That's the third one from the top. And you can see that the value is roughly above or below 10 transmitters, depending on the threshold level selected. The minus 20 decibel watt value ensconced in Auction 102 domestically exceeds all interference thresholds, no matter how few 5G transmitters are within the footprint of the satellite. Well, in this case, within the square kilometer that we're looking at. That's the dark blue line, the first one at the top on this graph. And then the only case that's shown on this chart, and I emphasize shown on this chart, that does not cross the interference threshold for the channel 1 4 gigs value for ATMS, even with 100 5G transmitters in a square kilometer, is the minus 57 dB watt case shown at the bottom in light blue. So this chart helps your understanding of the meaning of the various unwanted emission levels that different groups or regulatory bodies have mentioned. Now, as a side note, recent action in Europe and recommendations of the Electronic Communications Committee, or ECC, of the European Conference of Postal and Telecommunications, which is known by the French acronym CEPT, CEPT, elected to bring the more stringent ITU limits into force sooner for the countries of the European Union. It does appear that the European Regulatory Authority will require base stations to comply with the more stringent minus 39 decibel watt value by January 1st, 2024, instead of the September 2027 value as selected by the International Telecommunications Union. Let's have the next slide. All right, as I indicated earlier, not all agencies use the 23.8 gigahertz passive data for numerical weather prediction inputs in the same way. NOAA, for example, has an operational product called, and it's a mouthful, Blended Total Precipitable Water, or BTPW. Now, TPW is a lot more comfortable term, so you'll let me use the acronym. We'll all be happier. In simple terms, think of TPW as the amount of water vapor in a column from approximately the surface of the Earth to the edge of space. So in this product, data from about 10 satellites that are sourced from different countries are combined to create a smooth TPW image across the northern hemisphere of the Americas. Gaps are filled in with a few non-microwave based sensor inputs. So this image-based product, it helps forecasters understand where there is potential for strong flooding or severe weather when the percentage of TPW is high. Conversely, when that percentage is low, it's an indicative that the area is subject to high fire hazards and potential fire danger. So this kind of a product is used to understand the transfer of moisture from the ocean to the land. Let's go to the next slide. The next slide, we're going to address some contributing technical factors that I think are areas where more information and more dialogue is needed. Let's go one more slide. The first one is really about the spectrum itself and the out-of-band emission levels from 5G systems. As I mentioned earlier, during the regulatory process, little information was available about the actual measured emission levels occurring for out-of-band from the 5G radio access nodes in the millimeter wave bands. Now, a signal could have a gradual fall off of out-of-band emission similar to the top graphic. In that, you see three sections, a main channel and two areas of adjacent channel where the fall off legs you're going to see. And the pink area shown in that top graph would represent the passive band 23.6 through 24.0. So you'll notice the reference point, the dot in the very corner, it's a single point, meets the regulatory requirement of minus 13 dBm per megahertz, which is also minus 20 dBW per 200 megahertz. But no one really knows how fast, how slow, or how fast that signal will fall off as it moves further and further away from the 5G signal. The bottom figure in this chart exhibits less out-of-band signal level. One simply does not have enough actual data to understand which of these figures is more representative of 5G tower transmissions. Let's do the next slide. The second thing to deal with would be the spatial considerations, the actual features and capabilities of a 5G antenna. The very first set of mathematical equations you see are representative of the single element pattern. The original analysis done at the ITU utilized signal element patterns to model 5G systems. But it's fairly clear from the technical literature the potential use of radio frequency beamforming is going to be adopted so that signals are focused and generated from an array, and they then would work to really improve the range and the coverage of the main beam signal of these millimeter wave transmitters. It certainly is possible that signals offset from the main will be offset in geometry as well as frequency, as you see in the third installation. Granted, the main beam may be more of what's termed a pencil beam, or I believe it was called a rifle shot. You certainly will have some of these other elements offset from the frequency. And, you know, if this is being used as a small cell, that all may be pointed in just the directions and steered appropriately for its coverage. But if it's functioning to cover a broad area, as in the last figure on the right, you may see these mounted such that you're covering 320-degree sectors from a cell tower, much like a standard coverage. So, there's some uncertainty in understanding how things will be implemented, how dense they'll be implemented, and what those patterns look like. Let's go to the next slide, please. Okay, the last issue that I wanted to talk about, we mentioned also earlier, and there hasn't, I don't know, been a lot of work done in this area, but it's called the upwelling of the signal component. The signals from an array supporting RF beamforming can be electronically steered, and those main beam 5G signals can be optimized in the frequency band of interest to communicate, track mobile handsets and user equipment. So those signals may bounce off the ground, they may bounce off existing buildings, they may bounce off the terrain before they reach their intended target. And some amount of that out of frequency energy will move in an upwelling direction. That emission can be intercepted by the passive microwave sensor. And it's that component of the signal that would be the source of any interference or contamination. Now, the movie at the beginning of this presentation was perhaps the easiest illustration of upwelling information that can be seen by the sensors. I won't go into detail with the example shown in this slide, but the slide does the technology in a slightly different scenario. That's one of existing satellite broadcast signals reflecting off the ocean surface near coastal regions into descending polar orbiting satellites as they move from the North Pole downward towards the US. This mechanism certainly can occur as well from the interception of dense terrestrial 5G signals out of band emissions upward into a passive sensor. Let's go on to the next slide. Our presentation has discussed numerous out-of-band emission values and talked about the unknowns associated with a number of technical parameters. Now, more information is needed to truly understand this issue. A dialogue between the 5G community and the weather and science communities would be very useful in understanding the potential impacts on microwave-based passive measurements from space. How dense are the 5G installations in any given area? How much signal from the 5G infrastructure moves in an upwelling direction that can be detected by satellites? How quickly will the adjacent band emissions from 5G transmissions fall off as they traverse? Will the RF beamforming contribute more or less to out-of-band emissions? If contamination is not identified in the data sets generated by passive microwave sensors, what will happen when such data is used in meteorological products? Since all countries freely share all other satellite measurements, how will such 5G emissions impact the use of passive measurements in all countries' products? Each sensor may have a slightly different footprint or sensitivity or different bandwidth and detect contamination differently. I think that's especially true when you start looking at the difference in how the European organization, the ECMWF, the European Center for Medium Range Forecasts, and their so-called Euro model utilizes some of these bands differently than perhaps somebody else. But those same models are used by domestic forecasters right alongside Euro models, and the combination of those outputs are utilized to make, forecast and warning decisions. So you cannot just simply look at the US satellites that may be impacted in a certain band, because you're now using products developed not only from US satellites, but foreign satellites and foreign models that may not work quite the same as in each country. Now, we've talked a lot about how to deal with this problem by reducing the emissions of a 5G system. There are other ways to look at this. One way certainly is to consider time sharing of the spectrum. What I mean by that, instead of forcing the 5G infrastructure to adhere to a rigid out-of-band emission limit, why not timeshare the band such that 5G transmitters within the footprint of all satellites as they come overhead will change frequency to avoid the passive bands? Now, systems right now can switch back and forth between 4G and 5G, so this implementation might be something to consider. That way, the emanation levels of 5G infrastructure could be excessive, but if the satellite's not there to look at it, then it may not cause any issue. those are things we should at least investigate and determine if they're feasible now and in the future. Let's go to last slide, which I believe is my summary slide. So we've discussed how different radiometers on weather satellites work as compared to communication receivers. We've also considered that spectral out-of-band levels, spatial characteristics, and how much of the out-of-band signal will move in an upward direction are three items that merit discussion between the 5G and weather communities and certainly require further due diligence. This contamination issue will occur slowly as the 5G build-out density increases. And time sharing should be explored as a potential solution to this problem, in addition to examining the feasibility of reduced out-of-band emission levels. I believe, and I hope, that this has added to your understanding of the complexities of this topic. I would be happy to take additional questions. And again, I want to thank you for your time and hope that you and your family stay safe as the country deals with the coronavirus pandemic.
Thank you so much, Dave. We really appreciate you taking the time. Please go ahead and send me your questions in the chat box. In the meantime, I think that we have a poll question that's going to pop up in just a moment. It is, just bear with me. Should we protect passive bands with a different criteria than is normally applied to terrestrial communication signals? Go ahead, look for that, vote. And in the meantime, I'm going to ask some other questions to Dave since we have him here. So I would like to know, you mentioned that this will affect meteorological organizations. What do you think is the biggest impact of the 5G interference adjacent to the passive bands?
Well, again, I think it depends on which bands, and the answer may not be the same for all countries. You have the international recommendations from the ITU, where they're going to recommend bands that they want to homogeneously use for 5G in the millimeter wave range throughout the world. And then you have actions that an individual country certainly can take in addition or an exception to that. And an administration is allowed to have something that differs from the international recommendation as long as it doesn't impact adjacent administrations and those administrations which are following the international rules. The IT radio regs are updated every number of years. It is a treaty obligation of the member. So it's one thing to have issues in the water vapor bands at 23 gigahertz. It would be a totally different problem and probably a much worrisome problem if they were to impact bands that do vertical temperature measurements in the 50 to, say, 58 gigahertz range.
Great.
I don't know how many people appreciate that numerical weather prediction models are doing a mathematical model of the entire globe's atmosphere. And to do that and to make those equations work, which cannot be solved directly, takes good initial starting conditions. And the lion's share of that data comes from these microwave passive satellite measurements.
Great. Thank you, Dave. We have a couple questions that came in. Hopefully you can hear me okay.
You're fine.
Great. Okay, so Ben asked, he said, great presentation first off, which I agree. Thank you so much. Have any of the telecom providers engaged in further discussion on the time sharing concept?
Not to the best of my knowledge. I don't believe. I wouldn't have firsthand knowledge of that, but I've not heard of that from any entity.
Okay, you said you wouldn't have knowledge of that.
I would probably be aware eventually if someone made that inquiry. That's why I say to the best of my knowledge. I'm certainly not the person one would contact, but I have not heard of it.
Yeah. Sorry, Dave. You cut out just a little bit there. I just want to make sure that we got your answer. Next question is from Lena Cashin. Is the 5G community and weather scientists talking together?
Well, there were original plans to try to solicit some discussions in a National Academy of Science session last year. But that session was not scheduled, did not happen. So again, I do not believe there are any discussions. You have to appreciate too that these systems are being conducted or being developed. They're not totally operational yet. So Whether the 5G community understands the actual measured properties of these systems is a good question. You obviously have to have built some test systems or some example systems to be able to give some of those characteristics.
Okay, great. We have another question from Steven. What are the other options for gathering the relevant weather information outside of the passive microwave detection?
Well, there are a couple of these bands where there may be some alternatives where you could measure it differently. But for the most part, there aren't alternatives. And the reason I say that is, if you take an infrared image taken from space, it's basically measuring down to the cloud tops. It's only going to measure until there's something impeding its ability to see. If it's a cloudless day, the satellite with an infrared or visible sensor will see all the way to the ground. But if not, it's impeded. Whereas a microwave sensor can pass through all those things regardless of whether it's night or cloudy. It's important that sometimes to take that microwave-based data, like when you're trying to characterize the interaction of a hurricane. Yes, you can do it by flying a Hurricane Hunter aircraft through the center of it and dropping a radiosonde. And of course, you can get some profiling of the atmosphere by radiosondes, but they're launched twice a day at a small number of locations throughout the United States. That's not enough to characterize the entire volume of the atmosphere. Mm-hmm. You can take some GPS radial occultation measurements, but they don't quite work the same way and cover the same geographical volume of the atmosphere. So microwave measurements, like I said, being the major input to some of the models as shown by the ECMWF and also by NASA's GMAO group on their website, I think that would be very difficult to replace, in my opinion.
Thank you. We have another question. Lauren asked, first of all, she said, thank you so much for your presentation. She said, do you know how much weather forecasts will be impacted by the new WRC 24 gigahertz OOBE limits?
No, not precisely. As I've described in the presentation, those limits, first of all, have to be applied. Like I said, most countries will pick up those limits. Mm-hmm. The Europeans certainly didn't feel like they were adequate in that they brought the more stringent limit forward several years, and that's a recent action. There was quite a bit of discussion in the spectrum management realm internationally about this, but I don't know really whether the scientists understand and have the ability to simply determine the impacts. Typically, you will see experiments done, observational experiments, where they would take a numerical weather prediction model and they would remove a certain category of data and then run the simulations again and compare them with what had actually happened. But it's not typical to take it out band to band. It's an expensive process. It's a complex process. And some organizations utilize multiple bands as a calibration or a data correction capability. It would be very hard, I think, in my opinion, to just take one band out and try to run it. It would invalidate perhaps other things.
Okay, great. I have a couple more questions. So what are the 3 factors in the design and implementation of a 5G network that could determine how weather instruments in space making passive measurements could be impacted?
Well, as I said, you don't know for sure what the out-of-band emission levels are. And as in any transmission or electronic system, the signal level should start, and as it moves away from the signal of interest where you're trying to, communicate 5G information into areas out of the band, it's going to certainly reduce. But it's going to reduce at a level that we don't quite understand. Now, if it were another communication signal that you were trying to prevent interference with, spacing, filtering, is certainly a factor that helps. But in this case, remember, we talked about on the one slide, you are detecting the very minute changes in the noise floor level. And a large signal or a signal component can raise that noise floor for some distance away from the frequency where it's intended to be used. So in that case, you certainly could have impacts from these kind of scenarios because the radiometer, which is a square law detector on the spacecraft, works so differently than a communications receiver.
Does not directional nature of 5G transmitters protect the noise floor of the critical WX forecast frequencies?
Well, again, I'm not an expert on radio frequency beamforming, but as you saw in the opening graphic, it's my understanding that you don't actually have to be line of sight with a outdoor receiver or a handset to communicate at these millimeter wave frequencies in a 5G infrastructure. And so they can electrically steer in these small arrays, this RF beam created signal, to optimize it. And then in doing so, you get that bounce around the corner, type of event. And at the same time that you're optimizing the signal that you want for 5G, you're going to create some out of band byproducts. It's just how it's going to work. And they don't have anything to do with communicating the 5G information. And they may, as you saw on the one slide, be at a different angle and certainly at a different frequency. And if they're far enough over that they can be seen by the satellite and enough of it bounces or reflects upward to a satellite that itself has a complex scan, it isn't just looking straight down, that's the mechanism that causes the masking of the actual desired measurement by the weather sensor.
Great, thank you. We have some more questions. Bruce asked, will it be possible to monitor the level of 5G emissions into the EESS band and pinpoint the source of any levels that exceed what's permitted? In other words, will it be practical to identify and resolve interference?
I think it can be identified. I think that would be an extremely good role in the short term for a small sat-based sensor or an aircraft-based sensor, because 5G around the world will roll out at different time frames and frankly in different parts of the spectrum. Here in the United States, we auction frequency pairs starting at 24.25 gigahertz all the way through 27.5 was the band that was allocated, but it wasn't all sold that way. In other countries, perhaps they would allocate less spectrum. I believe, if I'm not mistaken, in the European Union, the EC directive said that all countries needed to do at least 1 gigahertz within the 24.25 to 27.5 range, a lot more than a gigahertz in frequency if you do the math. I know some countries have looked at the top end at 26.5 to 27.5. That's most likely far enough away from a weather sensor frequency as to not be a really big issue. So the devil is in the details, so to speak. Depending on where you place the licensee in the band, how they build the system, they may or may not know exactly how much out-of-band emission levels they have. Other than the single level at a single point that you saw on the one slide, it's difficult to predict what they're going to do as you move further out in frequency and into the midst of a passive band.
Great. We have another question from Michael. Also, he said, great job, David. He said, is it too late to mitigate the effects of 5G interference on weather data and forecasts?
No, I don't think it is. I think, though, you first need to understand what the scenario is. You need to have some actual data on the systems. You need to understand if the data would be different from system to system. Is it something unique in the way one installs a given tower that you may get more or less out-of-band emissions, or if you drive it via software in a certain way to create a type of primary signal? These are things that we don't really understand. And unless you've had some extensive hands-on experience with the production 5G radio access node, I wouldn't know why you would know.
Right.
There are the time sharing mitigation, I think, is certainly a possible alternative. And as I mentioned in the slides, since many of these systems are already designed or would be designed to switch from 5G to 4G, because after all, if you had a smartphone with millimeter wave 5G and you moved out of the coverage of it, the system's probably going to automatically switch to 4G. And it's not just going to drop your call. So the systems are somewhat designed to go back and forth anyway. So as long as they knew where the satellites were and they had the orbital information and they knew when to shut off or change frequency, I'm sorry, shut off is the wrong word. I mean, that's certainly a viable approach that should be investigated, should be looked at.
Great, thank you. We have one more question. So in January 2020, during the annual convention of the American Meteorological Society, the Aerospace Corporation released an issue paper, which is the same title as our presentation from you today. What message were you trying to convey? What's the key takeaway that you want to leave our audience with today?
Well, again, I think we were trying to raise a little bit of some of the understanding of topics like we discussed here. As an issue paper, it does quite get into the level of technical detail that one might need to understand all the issues. But we were trying to, again, grow the appreciation for the complexities and the differences involved in a radiometer making measurements from space versus a radio receiver trying to process a communication signal. As you unwind this, many aspects to them. And how large a problem it is or is not is going to depend on the details and understanding whether there could be something done to mitigate issues if there are issues, understand how licensees would adopt through any regulatory changes, any of the new international guidelines that may or may not, future bans that may be selected. You have to look at the broader picture. As we indicated earlier, many of these organizations utilize these various passive band data in different ways, and some use them in concert with other bands for adjustment of the data, correction of the data. Maybe you need to remove the water vapor values from some other band before it's of value to you. So it's not a real simple answer, and the details of that are probably outside my wheelhouse.
Okay, great. Well, thank you so much, Dave. I asked Colleen if she has our poll results. We might have had a little glitch there. So if we don't have that, I'm just going to keep going. Well, thank you so much for joining us, Dave. We're really glad to have you. We really appreciate you taking the time to speak to us. Our next episode is on what the expiration of New START could mean for U.S. Space Forces with Mick Gleason. Please be sure to go to aerospace.org/policy. You can click the Watch the Space Policy Show button. You can check out our papers, our experts, our events, and be sure to sign up. Until next time, thank you, everybody.
Thank you.